Good morning, everybody. My name is Sergey. I'm coming from TU Berlin, and today I would like to share with you our work in the area of automating data quality validation for dynamic data ingestion. First, let me start with the motivational example. Imagine a data engineering team at a retail company that maintains a search engine for products. They regularly collect, pre-process, and ingest product data from web crawls, key value stores, or data pipelines from other teams in order to index this data and keep the search engine up to date. Note that these data sources rarely implement any integrity constraints, as it would have been done in traditional relational databases. If another team introduces errors in the data pipeline, issues like missing values or wrong encoding might lead to the products not being indexed correctly. And as a result, products might end up in the wrong category or not appear in the search feed at all. Errors in data arise either from the data generating process, where we are initially collecting the data of unsatisfied quality, or from data preprocessing, where we're receiving the high quality data and corrupting it in any way in the data pipeline. In practice, error detection and data quality validation mechanisms are applied as a countermeasure. However, all these solutions require either domain expertise in the form of rules or patterns, or labeled examples for the algorithms to learn what records are of acceptable data quality. The problem becomes evident in cases where domain knowledge is incomplete, and even experts do not know for certain what data is of high quality, or when monitoring a data stream by the domain expert is too costly or time-consuming. It becomes more challenging with the data changing its characteristics over time. We looked at the common real-world use cases and made the following design decisions while working on our approach. First of all, we work with the tabular data that comes regularly in batches. For instance, daily data ingestion in our retail company example. Then we consider historical data to be of acceptable data quality. This assumption is crucial. It means that at the time t, we allow ourselves to use the data from time 0 to time t-1 as the training set that models the data of high quality. If this assumption seems counterintuitive, let's get back for a moment to our motivational example. For the retail company, products that are placed in the wrong category or not appearing in the search results at all lead to negative customers report or low service ratings. To put it simply, should anything bad happen, we would have already learned about it, as it affects business KPIs that are usually very carefully monitored. As the last assumption, we consider that in case errors occur in the data, they most likely affect a fraction of the batch. For instance, the missing values or wrong encoding will affect the whole batch of data rather than a single record or a single cell. To explain our approach, let me draw a simplified example. We have a daily ingestion of data, and today is day t. 3 days ago, we retrieved a table with 2 columns, one categorical and one numeric. For every attribute of the incoming data batch, we compute simple descriptive statistics, such as completeness, the number of approximate distinctive values, mean, standard deviation for the numeric data types. These statistics can be computed with a single pass over the data. We record these values over time, and we train a novelty detection algorithm that learns the characteristics of acceptable data. For the upcoming data partition, we compute its feature vector and let the model decide whether it is similar to the previously observed data partitions or not. We do not aim to detect high granular errors. Our approach enables a proactive alerting system that makes a decision whether the whole data batch is of acceptable quality. In this particular example, a missing value in column A and a numeric outlier in column B affect the completeness metric and numeric statistics, that in turn raises an alert. We evaluate our approach against 3 baselines: TensorFlow data validation, the DQ library, and statistical testing. For the first 2 solutions, we consider both the automated and the hand-tuned variants. On 2 real-world datasets, our approach outperforms automated tools, which turned out to be rather conservative in their predictions and treated any change in data characteristics as a signal of data quality issues. The figure shows that our fully automated approach performs on the level of manually curated alternatives, DQ and TensorFlow data validation. We also measure average execution time that the candidates took to make a decision. Due to the low computational complexity of our approach, it performs at least 1 order of magnitude faster than other baselines, which is a nice benefit for scenarios with frequent data ingestion. Furthermore, we evaluate how well our approach performs depending on the error magnitude and when the training set grows over time. On 3 datasets with synthetically generated errors, missing values, numeric anomalies, swapped fields, and typos, we observe 2 patterns. We have either similar predictive performance regardless of the fraction of errors, so flat lines, or gradual growth of predictive performance with distinctive, more rapid increase for fractions up to 20%. The figure on the bottom shows that the predictive performance does not improve significantly over time with the growth of the size of the training data, in the majority of cases. To summarize, I would like to address several points as a takeaway message. First, data quality validation is crucial for establishing trustworthy data pipelines. The most challenging scenarios are the ones where domain expertise is incomplete and data might change over time. In these cases, existing solutions, either in the area of error detection or data quality validation, perform poorly. And we demonstrate that collecting simple descriptive statistics over the data and analyzing them with novelty detection methods makes it possible to distinguish critical errors in data. It does not require domain expertise and adapts to changing data. As for future work, we consider investigating more exotic types of data quality issues and prepare benchmarking datasets for data quality validation specifically for dynamic data. If the topic of data quality validation is close to your heart, or if you're facing challenges that I outline in this talk, I invite you to take a look at our paper for more details. With that, I want to conclude the talk and thank you for your attention.